Welcome to Algebra 2, Semester 2, Unit 11, Section 6.4. In this unit, I'm just going to back up just a little bit in case you haven't been in class. We did a little activity, a graphing activity, or I intended to with you. So if you have been in class, you're welcome to come back and do it tomorrow. Before you do this section, you'll know what your timeline is, whether or not you have that kind of time. If not, then do it with me right here. Grab a piece of graph paper, make a grid, just like I have. And our first thing is that we're going to graphically show you what the inverse of x minus 3 over 2 is. And basically, we want to go ahead and graph this and then just show you graphically what the inverse looks like. So to graph it, I would convert it into slope-intercept form. So it's 1/2 x minus 3/2. And I would put y equals. Okay? So now we could go ahead and put our y-intercept at -3/2 and then our slope at 1/2. But in some ways, that might cause a little bit of confusion just because -3/2 is a fraction. And I want to be as accurate as we can on here. So we can't always go to a T-chart. We'll just give ourselves a couple points here. So let's say that x is equal to one. If x is equal to 1, then 1/2 minus 3/2 would be a -2/2. So written in whole number, that would be our point 1, -1. Now let's say that x is 3. Just get a couple points for graphing here. If x is 3, then we're going to have 1/2 times 3, which is 3/2. 3/2 minus 3/2 is 0. So that would be 3, 0. Yeah, just with those 2 points, we could go ahead and graph this line. So we have the point 1, -1, 1, -1. Remember, the first is always your x value. I'll try to keep it on the camera while we graph it. This is your x value, this is your y value. So we go over to +1 on x and down to -1 on y. There's a point. And then our next one is 3 on x and 0 on y. So we go 1, 2, 3, 0. Okay, so this is our line. I'm going to move it slightly so that we can extend that line. I know that I have a ruler here. Let me just find it. There it is. Okay, so we extend this line clear across the graph. Remember, I like you to do that. We do see that we've got a positive slope of 1/2, and our equation had a positive slope of 1/2. So we can rest assured that that line is representing that equation. Okay, and just to double check it, has a slope of positive 1/2, so that means from one point to another on the line, it will rise 1 and run 2 to the right. That seems to be correct. We have a slope-intercept, or I mean a y-intercept of -3/2, which is -1.5. That looks approximately right as well. Okay, now in inverses, what we do to find the inverse is we swap the x and the y value. So our inverse can be written as f to the -1. That means we're going to swap our x and y. So we take our y, we replace it with an x, and we have 1/2 y minus 3/2 for this equation. Now we need to get the y alone, so we'd add 3/2 to each side. We get x plus 3/2 equals 1/2 y. Now we need to get the y alone still, so we would multiply each side by 2 to get rid of that 1/2, we would have 2 times a half is equal to 1. That gives us y. That's the whole reason we did it. 2 times x is 2x. 2 times 3 halves, the 2's would cancel, and we would get plus 3. Make sure to do that with me if I confuse you by doing it in your head. Now we can write the y on the other side. Y equals 2x plus 3. This one we can easily graph with whole numbers onto this graph. So we go to positive 3 on the y-axis. From that point, we do our slope of 2 over 1. It is rise 2, run 1 to the right because it's positive. And now I'll put it in a different colored pen just so that we can see that that's the inverse. We can compare our lines, maybe a little bit easier that way. So we would write f negative 1 on that line. And we would have this other line labeled as just our regular f of x. So we can see that those two are inverses by the equation. In addition, if we wanted to look at the points, they're inverted. If we plug in negative 1, see we had negative 1 for y in our original. If we plug negative 1 in for x, in order for it to be an inverse, we should get what the y value was, or what the x value was in the last one. So it should come out being 1. Let's check and see if it does. 2 times negative 1 is negative 2, plus 3 is 1. Now, if we plug in the 0 from the y and put that on x, we should end up getting 3 for the y. 0 times 2 is 0, and 0 plus 3 is 3. So you can see it in the equations, how we've just flipped the x's and y's. Then you can check it in your t-chart because they should be exact opposites. It should be 1, negative 1, and here it will be negative 1, 1. Here it will be 0, 3. So our x and our y's are flipped. Now, to show you how that shows up graphically, since we are saying x is equal to y and we're flipping them across there, we simply plot the line x equals y, which, if you remember from Algebra 1, is a direct variation. Sorry, I got to make sure that I'm on all the points, and I'm not. It goes in an exact diagonal. It is also called the parent function. So that is y equals x, because you do that in your algebra. You absolutely transfer y for being equal to x in your inverses. Now watch what happens here. This is so cool. If you highlight, sometimes it's easiest to see that line highlighted, and realize that's the line for which we're proving that they're inverses. Now if we take the points that we just related and we draw a line to them, connecting them, so 1, negative 1 is equal to, let me find it here on the inverse, negative 1, 1. And now we connect those 2 points. You might notice what happens as we connect a line between them regarding this inverse line. Do you see how it's perpendicular? And it's exactly the same distance. It's a diagonal of 1 square away from our inverse line, and that one's a diagonal of 1 square. So now we look at 0, 3, and 3, 0. Here we have 3, 0, 0, 3. So we connect those 2 points. And again, they form an exact perpendicular to the inverse line. They are 2 or 1.5 diagonals from the inverse line, 1.5 diagonals. They're exact same difference, and they're at a perpendicular. Now at this point, we didn't have the inverse plotted over here as a point, so I'll plot it. It is 1, 2, 3, 4, 5. So it is 1, 5. That means that the inverse over here should be 5, 1. 1, 2, 3, 4, 5, 1. Those are the inverse points on the graph. Now let's draw the perpendicular and make sure that they graphically are the same distance from the inverse and perpendicular to our y equals x. It certainly looks like they are. We'll count it. There's 1, 2 diagonals, 1, 2 diagonals, and it is perpendicular. So that's how inverses show up graphically. That just kind of really allows you to see what we're doing here. Is we're giving you one function, you're finding the inverse of it. So the inverse of f of x is f to the negative first, which is simply stated as the inverse function. Here it says, find the inverse function of 3x minus 5. So we simply swap the x and the y, and we have x equals 3y minus 5. Now, do me a favor, just turn it around so the y is back on the left-hand side. So we have 3y minus 5 equals x. Now get the y alone. In order to get it alone, we would add 5 to each side. We would get 3y equals x plus 5. Now, in order to get the y by itself, we have to divide by 3. That means we have to divide each of these by 3. So we end up with y equals 1/3 x plus, 5/3. And that is our answer. That is the inverse, just by swapping those back and forth. On the following graph, highlight the xy line. So we'll go ahead and do that right now. Remember, the xy line is that direct variation, parent function of y equals x. So it is an exact diagonal. It'll go through the origin, and it will be right through 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Make sure and mark it y equals x. Now what they're having you do is they're having you plot the equation 3x minus 5 on this graph, and then they're going to have you prove that what you just developed as your inverse truly is the inverse on the graph, just like what I just showed you. So we have y-intercept of negative 5, so we'd come down to negative 5 and put a dot. Let me go ahead and put that is 0, negative 5, just to make it easier for when we find inverse points. Okay. Now the next thing is our slope is 3/1. So from this point we rise 1, 2, 3 and run 1 to the right. That point is 1, negative 2. Okay. So with 2 points on a linear graph, that's enough to graph those. Okay. Now we can simply graph our inverse by counting the perpendicular line here. Or we can do the inverse by looking at the points. It's going to be negative 2 for x and 1 for y. So at negative 2, positive 1, we should have a point. And for the inverse on this one, it would be negative 5, 0. So it'd go negative 5 on the x and 0 on the y. So it's negative 5, 0. And we should be able to connect this, and it should be a complete inverse. Now, the one thing that I forgot to do was label this as f of x. Label this as our inverse f of x. And now we look at the points and see, are they perpendicular? Are they same distance from the y equals x line? So we'll draw a perpendicular here from point to point. Draw a perpendicular from this point to that point. And let's see. This one is 1, 2.5 diagonals, and here it's a half, 1, 2. So 2.5. And it is perpendicular. This one looks to be perpendicular. It is 1.5 from the diagonal, and this one is 1.5. Okay, so it does seem to be an inverse. We can say that that checks that line. Now we should also check and make sure that it fits that line. So this f of negative 1 has a slope of 1/3. Let's make sure that it does. From this point to this point, we rise 1 and run 1, 2, 3 to the right. So it is 1/3. That checks. It has a y-intercept of 5/3. 5/3, if we divide 5 by 3, is 1, with 2 left over, so it's about 1 2/3 between 1 and 2, and it does seem to cross the y-axis at that point. So 1 2/3 seems to check. Okay. Now it asks, are these inverse functions? Well, there is another way that we can verify whether or not inverses are inverses. And here's how we verify. If we take the f of the inverse, it will equal x. And then if we turn around and we take the inverse of f of x, it will equal x. So in other words, we're going to take composites of these, and they should end up equaling x. So basically, we're going to take this and plug it in for x over here, and then we're going to take this and plug it in for x over here. And they should end up equaling x. So let's try it. 3 times, now we plug in this value, 1/3 x plus 5/3 minus 5. Okay, we're looking for it to equal x. We distribute 3 to each of these. That would be 3/3 x plus 5 times 3 would be 15/3 minus 5. Well, 15/3 reduces to 5 because 3 goes in there once. 3 goes in there 5 times. 5 minus 5 will cancel, won't it? So we end up with 3/3 x, which is equal to x. So that one works. Now we need to make sure that it works over here. Take our 1/3 instead of x, we plug in this function. So we have 3x minus 5 plus 5/3. Okay. We distribute 1/3 times 3x would be 3 over 3x. 1/3 times negative 5 would be a negative 5/3 plus 5/3. Well, a negative 5/3 and a positive 5/3 will cancel each other out, and we have 3/3 x, which equals 1x. So they are inverses, and that's how we prove it. Find the inverse of each function. Well, in order to find the inverse, we put y in for the f of x, and now we swap the x and the y. We get x equals y plus 4. Turn the whole equation around. Y plus 4 equals x. Y equals x minus 4. We just subtract 4 from each side to get y alone. Go ahead and pause the video, do the next two on your own, and then come back and check. See if you have them right. This would be y equals 2x minus 1. Swap them. It becomes x equals 2y minus 1. Turn it around. 2y minus 1 equals x. Add 1. 2y equals x plus 1. Y equals 1/2 x plus 1/2. Okay. Y equals -3x plus 1. Now we swap this around, so we have -3x plus 1. Oh, I'm sorry. We need to swap our xy's first. X equals -3y plus 1. -3y plus 1 equals x. Subtract 1 from each side. -3y equals x minus 1. Now divide by -3 on each side. Y equals -1/3 x plus 1/3. Another way you could have written this is y equals x minus 1 over -3. Either way would work. Okay? So that one has two possibilities how you could show that. There's a couple more actually, so see me if you think you've got it wrong. Okay. Next page, we're going to graph some inverses. These are nonlinear functions, so it's kind of fun to see what happens with them as we graph them. This is x cubed. If you remember back to chapter 10, we did this. It is the parent function. So if you have to plug in points, you can. Remember, 0 cubed is 0. 1 times 1 times 1 is 1. And -1 times -1 times -1 is -1. And that's what we called our vertex when we were doing these before. And then 2 cubed was 8. So basically, if you remember right, it went kind of like this. Now to find the inverse of that, let's put on our inverse line. Remember, our inverse line is y equals x. It's the parent function of the linear graphs. So funny enough, our vertex lays right on this line. So it's going to lay right on our line for when we find the inverse. Let's algebraically figure out what our inverse would be. That would be y equals x cubed. Swap our x and y. That's going to be x equals y cubed. Bring our y to the right side by flipping the whole equation. Or left side, I mean. Now to get y cubed alone, in order to cancel a cube, we have to do a cube root. What you do to one side, you do to the other. So we find that y equals cube root x. And now I don't know if you'll remember from Algebra 2 Semester 1, you actually did this parent function. Or maybe you did this one in, I think you did this one in Algebra 2 Semester 1 and this one in Algebra 2 Semester 2. Anyway, the cube root of 0 is 0. Cube root of 1 is 1. Cube root of -1 is -1. But the cube root of 8 is 2. So this time, it's going like that and like that. So drawing those in two separate lines probably would be best. Goes something like that. And the other one goes the other way. So you can see if you were to bring in your perpendicular lines at any points out here, you're going to prove that this is a inverse. Right there in the middle, it's great. There's no distance across there for them. But that proves that it is an inverse. The y equals cube root of x is an inverse to y equals x cubed. Now let's look at the x squared. These are kind of neat ones to graph. It gets into some other stuff that we're going to look at in the next chapter. But let's graph our diagonal first thing. This is the y equals x. Because in an inverse, we say that we can swap the values. So that's your y equals x line. Now, in order to write the algebraic inverse, this one would be y equals x squared. So the inverse, f negative 1, or the inverse of the function, would be x equals y squared. Bring the y to the left-hand side, y squared equals x. To get rid of that y squared, we do a square root. And we have y equals square root x. Okay? So when we plug in 0 to this one, 0 squared is 0. Plug in 1, 1 squared is 1. Plug in negative 1 squared is positive 1, because negative 1 times negative 1 is positive 1. 2 squared is 4. And negative 2 squared is also 4. So now we draw what we remember, the parabola, like such. And now to do the inverse, looking for a different, I'll do it in pink, I guess. The square root of 0 is 0, so it would be right there, same place. The square root of 1 is 1, but then the other option, because remember when we do this it has to be plus or minus, the other option would be negative 1. Square root of 4 is 2, but the other option is negative 2. Okay, so our inverse lays like that. And if you draw your perpendiculars from point to point, you can see that these truly are inverses, simply transformed over that diagonal. Okay? So again, it proves to be an inverse function. Okay, next little bit. Find the inverse of the function, 2x cubed plus 1. I'd like you to do this and bring all the proof, showing me the diagonal, the function, the inverse function, and the perpendicular lines, as well as the equations. Please bring this to class with you to show that to me. I want to see that before you start on your bookwork. That ends this section. Thank you very much.